Bismillahirrahmanirrahim. Assalamu alaikum. Hello and welcome to lecture number 17 of Algebraic Topology. Our today's topic of discussion is homology groups of simplicial pairs. So in this lecture we will see what are simplicial pairs, how we will define homology of them, and in the next section we will see what is a collapsing and how collapsing will help us to calculate the homology. So what is a simplicial pair? We know what is a simplicial complex. A simplicial pair consists of a simplicial complex K together with a subcomplex L. Okay, so that's what it means. A simplicial complex with a subcomplex. The inclusion I, because we are saying that this L is subcomplex of K. In other words, every element of L is an element of K. In other words, we have an inclusion map. So inclusion map says that just take an element of L, let's say A, and it is the same. It gives me the same image. Okay, so let's for example take A to be equal to 1, 2, 3, 4 and B to be equal to 1, 2 and 4. Now we can easily see that B is contained in A. So I can define an inclusion map from B to A such that I of B is equal to B. Okay, so this map takes an element of B and gives the same element, and it will be an element of A because B is contained in A. So for example, I of 1 is 1, I of 2 is 2, I of 4, because that's the third element of B, I of 4 is 4. So 1, 2, 4 are elements of A. And similarly we can define inclusion map for these. Okay, now this I induces an inclusion homomorphism. Okay, so what is this? So this is basically the free abelian group generated by the Q simplexes of L, and what is this? This is the free abelian group generated by Q simplexes of K. Okay, now since L is contained in K, so every Q simplex of L will also be a Q simplex of K. So that's why let's say I have a Q simplex, let's call it delta, and I Q delta will be an element of CQK, because every Q simplex of L is also a Q simplex of K. So that's why we can define this homomorphism. So why this is homomorphism? Because as I said earlier, that I'm just taking an element of CQL and taking it as it is an element of CQK. So basically this is just identity. Okay, so if it is just identity, then basically this is a homomorphism. This can be proved very trivially. Okay, so that's how we define, given any simplicial pair, we can define an inclusion homomorphism. Now we already know that if we have a simplicial complex, then we have this chain complex. Okay, so when we were defining this object, then we didn't name it a chain complex, but in the last lecture we saw that this is in fact a chain complex. What is CQK? The free abelian group generated by Q simplices of K, and this is free abelian group generated by Q minus 1 simplices of K, and up to so on. And we also have these boundary maps. So how to define these boundary maps? So for example, if I have a 2 simplex, so for example this shaded triangle with elements E0, E1, E2, so so let's call it delta 2. So what is the boundary? Okay, so what is the boundary partial 2 of delta 2? So the boundary we can easily calculate. Basically it will consist of E1 E0 E1, E1 E2 and E2 E0. Okay, so let's see. So this delta 2 is basically equal to E0 E1 E2. So we can calculate the boundary. Okay, so first delete E0, so we will get E1 E2, and delete this one, we will get a negative sign, and E0 E2, and plus we have E naught E1. So that's how we calculate the boundary of this. Similarly, given any Q simplex, we can calculate the boundary, and the elements of CQK are basically free abelian group generated by these Q simplices. So in other words, the elements of CQK will be of the form A1 delta 1 plus A2 delta 2, where up to so on, and AN delta N, and where delta I are elements of basically are you can say are Q simplices. Okay, so these are the elements of CQK. Okay, so if these are the elements of CQK, then we know how to define the boundary of these simplices, but how to define the boundary of this general element? So we will use linearity of these boundary maps. So linearity means that partial Q of A1 delta 1 plus A2 delta 2. So I'm just going to prove it for two elements, and of course we can generalize it to n. So this is equal to A1 partial Q of delta 1 plus A2 partial Q of delta 2. Okay, so using the linearity of this, we can easily calculate the images of every other element of CQK. So these are the boundary maps, and we discussed them, we have dealt with them. Now similarly, if I have a subsimplex or a subcomplex of this simplicial pair, namely L, then once again we can define the same chain complex. So what is CQL? So the free abelian group generated by the Q simplices of L. CQ minus 1L is the free abelian group generated by Q minus 1 simplices, up to so on, and these are the boundary maps, exactly the same boundary maps. So given any Q simplex, I can calculate the boundary, and then I can generalize it to the linear combination, or sorry, the integer combinations of the elements of CQL. So we have two chain complexes. So now consider the following exact sequence. So we have already seen that this IQ is basically an inclusion homomorphism, because CQL is basically contained in CQK. So this is inclusion homomorphism. Okay, so in other words, we can add a 0 on this side, and we can say that this part is exact sequence, because the image of let's say this map F is 0 if F is homomorphism. So the image of F is 0, and which is equal to the kernel of IQ, because this is inclusion, this is injective homomorphism. So that's why this portion makes sense, that this is exact sequence. So that's why we can add 0 over here. Now consider this sequence. Consider this sequence, and where UQ. Okay, so we will define what is UQ, and what is this element CQKL. So let's forget about this discussion and see what it should be. Okay, because this is an exact sequence. If it is an exact sequence, then what this element should be. Okay, so the image of IQ is basically CQL, and it should be equal to the kernel of UQ. Okay, and once again, first isomorphism theorem of modules. So this implies that CQK quotient CQL should be isomorphic to CQKL. Okay, so this object is in fact isomorphic to CQK quotient CQL by just using the exactness of this this short exact sequence. Okay, so so that's why we can say that these elements CQK quotient CQL are basically CQKL. So that's why we say that these elements are CQK quotient CQL. Okay, now the homomorphism. Okay, so we know that these are the boundary homomorphism. So these maps the subgroup CQL to CQ minus 1L. Okay, so let's say this is CQK, and inside CQK we have CQL. Okay, and this group is basically CQ minus 1K, and inside this is CQ minus 1 L. Okay, now these boundary maps, so partial Q, so it takes CQ k to CQ minus 1k. Of course, it is a subset of this, so let's say this shaded region. Now the image of CQK under this boundary map is let's say this shaded region. Okay, so this shaded region is the boundaries of CQK inside CQ minus 1k. Now this CQ minus 1L is basically set of all Q minus 1 simplices, so the free abelian group generated by all Q minus 1 simplices of L. And we know that if I have a Q simplex inside L, then its faces, okay, so when I take the boundary, then I'll be considering Q minus 1 faces, and all the faces must be contained in this CQ minus 1L. So in other words, when I'm taking image of elements of CQL, then I must get an element of CQ minus 1L. So basically this set is basically mapped to, so this portion, okay, so this blue portion is basically the image of CQL under this boundary map. So in other words, this CQK, this free abelian group, maps to CQ minus 1, and CQL maps to CQ minus 1L. Okay, so in other words, if I have CQK quotient with CQ minus, CQL, then the elements of CQK maps to CQ minus 1k, and the elements of CQL maps to CQ minus 1L. So we can define this homomorphism, because the elements of this maps to elements of this, and the elements of this maps to elements of this. So we have a well-defined function which will be a homomorphism, so because this partial Q, this boundary map, is a homomorphism. Okay, so we have defined a boundary map partial Q from CQKL to CQ minus 1 KL. So since the homomorphisms are induced by the boundary homomorphisms, so once again we are just saying that if I have CQK quotient with CQL, so it goes to CQ minus 1k quotient with CQ minus 1L. So how we define this thing? So take an element of CQK, apply partial Q, and get an element of CQ minus 1k. So basically we are using just the boundary. So basically we are just using these boundary homomorphisms to define the maps between CQKL and to CQ minus 1KL and up to so on. Okay, so in other words, if I start from an element of CQKL, so let's take an element, let's say X. So when I apply partial Q, this map, and when I apply this map again, then I should get 0, because what I'm really doing is I'm taking elements of this quotient group, and if X is an element of this set, then X is equal to X plus, so basically X is equal to some element of CQK, so let's call it Y plus CQL, okay, where Y belongs to CQK. And how we define this map? So basically I'm just taking this image under partial Q of this Y. Okay, so I'm just taking the image of this, and of course I'm taking the image of this as well. Okay, so which is contained in CQ, so CQ minus 1L. Okay, so that's how I take image, and when I apply partial Q minus 1 on this element again, then I should get 0. Okay, so basically the classes in this quotient group are basically of the form this, and when I take image of this element x under this map, this homomorphism partial q, then I get an element, and when I apply this again, this boundary map, then I will get 0, because this is really coming from the boundary maps of CQ. And we also know that from these boundary maps we defined the boundary maps of this CQL and CQ minus 1L up to so on. Okay, so we defined these from here. Okay, so these are our main boundary maps, and from here we are defining these maps, and we are also defining these maps. Okay, so we are basically using the images of this chain complex, so in other words the images of the boundary maps of this chain complex. Okay, so we have the following commutative diagram. Okay, so we know that this is basically, so we have the following commutative diagram. Okay, so why this is a commutative diagram? Because IQs are just inclusion map, so that's why this diagram is commutative on this part. So once again, this CQL is contained inside CQK. So if I take an element of CQL and apply IQ on this, so I'm basically getting the same element, and taking this image will give me another element, and it should be the same as taking this element. So once again, what are these boundary maps of CQL? These are defined from the boundary maps of CQK. So they are the same maps, but they are just restricted to CQL. Okay, so if I follow this route and embed them, so once again this IQ minus 1 is just the inclusion map, so of course I should be able to get the same image, and that's why they are commutative on this part. And similarly over here what we are doing is we are actually calculating the boundary. So let's take an element x from here, so calculate this boundary and then take the quotient, or take the quotient first and then calculate the boundary. So that's why they are the same elements, because once again we are calculating the same, we are considering the same boundary map. Okay, so that's why this portion is also commutative. So we have this diagram as a commutative diagram. Now if I start from an element of CQK and apply UQ first, and then apply this boundary map, and then apply this boundary map, then it is the same as starting from this UQ, applying so the boundary map first, and then apply UQ minus 1, and then follow this path. Or I can start from CQK, apply this boundary map, apply this boundary map, and apply this thing. So these are all going to give me same elements. Okay, so once again, why this is the reason? Because once again we are using the same boundary map. So basically the boundary maps of the simplicial complex, of this simplicial complex, and that's why we are having this result. So either you can go to CQKL and then apply the boundary maps, because these are basically defined on the basis of these boundary maps. Okay, so or you can just follow these boundary maps and then apply UQ minus 2, or you can turn in the middle and then come here. So eventually you will get the same result. Also we know that if you apply partial q, so this is a chain complex, so if you take partial q composition partial q minus 1, then this must be equal to 0. So if this is 0, then we can say that okay, so this composition is also 0 because this composition, okay, so you apply UQ first, and this UQ is basically surjective. Okay, so why it is surjective? So because this UQ is CQK goes to CQK quotient with CQL. Okay, so that's why this is surjective, because we are taking elements of CQK and we are getting the classes of this element. So that's why we have this surjective. So using these two properties, we can say that the composition of any two boundary maps in this chain is 0. In other words, this is a chain complex. Okay, so once again, why this is a chain complex? Because the boundary maps, the composition of boundary maps, okay, and using the surjectivity of these maps, and if this is 0, then of course this is 0. So and of course these UQs are homomorphisms. So that's why we have this chain complex. So now we have the following chain. Okay, so we have these quotient groups, okay, and we have maps between them, which we just proved that they are basically homomorphisms. Now we want to show that this is in fact a chain complex. So in other words, we want to show that partial q composition partial q minus 1 is equal to 0 for all partials in which are the boundary maps in this complex. Okay, so why this holds? So due to this main fact. Okay, so in other words, starting from CQK and then applying UQ, applying this partial q and this partial q minus 1, or starting from this CQ, applying this boundary map, applying UQ minus 1 and then applying this thing, or starting from this CQK and applying this boundary map, and this UQ minus 1. So we should get the same results. So using this fact and using the fact that this is a chain complex, so in other words, in this case we have that the composition of any two boundary maps is 0. So and using the fact that these UQs from CQK to CQK quotient CQL, which is in fact CQKL, is basically a surjective homomorphism. Okay, so if it is a homomorphism, then it must take 0 to 0. Okay, so so this composition, okay, so this composition is 0 over here, and this will take 0 to 0. Now this is the same as first taking this root and then applying these maps, and so the composition of this must be equal to 0 because these two roots give me the same element, and this is surjective. So basically we are talking about each and every element. Okay, so CQ to CQK to CQKL is a surjective map. So in other words, take any element and there will exist an element in CQK such that that element, let's say x, is image of some element of CQK. Okay, so this x is equal to UQ of some element y. Okay, so y belongs to this. So we can start from y, follow these roots, and we will get 0. So in other words, when we apply this partial q and partial q minus 1 on this x, then we must get 0 because x is equal to UQ of y, and then we can follow y around this and we should get 0. Okay, so that's why these elements imply that this composition is 0. In other words, we have this chain complex. So we call the boundary homomorphisms as the boundary homomorphisms of the pair KL. So using maps UQ for q belongs to z, we get the following chain map. Okay, so first we have this CQL going to CQ minus 1L going to CQ minus 2L up to so on, and then we proved that we can define inclusion homomorphisms from CQL to CQK, and similarly for CQ minus 1L to CQ minus 1K, and this is named as IQ minus 1, and similarly CQ minus 2K, and this is named as IQ minus 2, up to so on. So this gives me I star, okay, so which is basically a chain map from basically the chain complex L to the chain complex K, okay, and this will give me a chain map from C star L to C star K. Now we have UQs from CQK to CQKL, so this is UQ, and we have UQ minus 1 from CQ minus 1K to CQ minus 1KL, up to so on. So UQ minus 2, CQ minus 2KL, okay, and this is a commutative diagram. So we already show that how this is a commutative diagram, okay. So these UQs, okay, so will give me the following chain map. So it will give me U from C star K to C star KL, okay. So we can define this chain map from C star K to C star KL, and why this is a chain map? Because we know that this is a chain complex, this is a chain complex, we have already shown, okay, and these diagrams, so this portion is commutative, we have already shown that. So that's why this will give me a chain map between these two chain complexes. And once again we also have this I, which is a chain map from this chain complex to this chain complex, okay. So basically we have this diagram which is commutative and with I and U's. Now we have also proved that this C star KL is a chain complex, and we know that from our results from homological algebra that if we have a chain complex, then we can define homologies in that chain complex. So now we can see that we can define homologies HQKL, which is equal to ZQKL quotient with BQKL, okay. So so this is partial Q minus 1. So of course what is ZQ? So ZQ is basically the image of, so what is ZQ? So ZQ is basically the kernel of this boundary map, okay. And similarly what is BQ? So BQ is basically the image of this partial Q plus 1 of CQ plus 1 KL, okay. So how these are defined? So basically these are the elements of CQK, okay, KL, so CQKL, which goes to 0, okay. So what are the elements of CQKL? Because CQKL is equal to CQK quotient with CQL. So what will be the elements of CQKL? So they will be of the form C plus CQL, okay. So there should be L over here, okay, such that C belongs to CQK and partial, so the boundary of this C belongs to CQ minus 1L, okay. So let's see why it is this. So this map partial Q is from CQKL to CQ minus 1KL. So we have already seen that CQKL is equal to CQK quotient with CQL. So what is CQ minus 1KL? So CQ minus 1KL is CQ minus 1K quotient with CQL, so CQ minus 1L, okay. And we are saying that this element, which is C plus CQL, goes to 0. So what are zeros in this CQ minus 1KL? So 0 means it should be an element of CQ minus 1L. So that's why we are saying that it's an element of so C is an element of CQK such that its boundary belong to CQ minus 1L. Okay, so similarly, what are the images? So the boundaries are basically image of this map. Of course, it means that the elements will be of the form partial q plus 1 e plus CQL, where e belongs to CQ plus 1 k. So once again, why it is the case? Because CQ plus 1 k is equal to CQ plus 1 of, okay, so let me write it down here. So CQ plus 1 KL is equal to CQ plus 1 k quotient with CQ plus 1 L. Okay, so that's why we are saying that an element of CQKL will be image of some element of CQ plus 1 KL if there exists an element. Okay, so E belongs to CQ plus 1k, so belonging to this element, such that it becomes partial q plus 1 e plus CQL. Okay, so what we have done is, considering this chain complex, we can define at any CQKL, we can define the image and kernel, and the image and kernel are a little different because we are dealing with quotient groups over here, or quotient modules, because these are abelian groups. So these are quotient groups. So using the properties of the quotient groups, we can write down the kernel and the boundaries like this. Okay, so we can define homology groups of this chain complex, which is basically a chain complex defined from the simplicial pair. Now we have already seen that if we have a short exact sequence of chain complexes, then it will give me a long sequence of homology groups. So we have proved that this C star L with this I map, and C star K, and this with this U map goes to C star KL. Okay, so this is a short exact sequence, and from this short exact sequence we can define this sequence of homology groups. And what about these maps? Okay, so the proof is already done, because we have already shown that in homological algebra, if we have a short exact sequence, then we have this long sequence of homology groups. So what about these maps? Okay, so let's see if these maps are well defined, or how these maps look like. Okay, so consider this map HQKL to HQ minus 1L. So starting from this point and going to this point. Okay, so let's see if these maps are well defined or not. So how to show that these maps are well defined or not? So take an element Z from HQKL. So what is the HQKL? So HQKL is basically ZQKL quotient with BQKL. So ZQKL is basically the kernel of this boundary map, and BQ is basically the image of this partial q plus 1 of the elements of CQ plus 1 KL. Okay, so Z is an element of HQL, and there exist, so suppose that there exist two elements, C and C prime, belonging to CQK, such that Z is equal to C plus CQL, and which is equal to C prime plus CQL. So why there must exist a C? So because we are assuming that there exists two C. So let's see why there must exist one C, because this map UQ is surjective. Okay, because this is a short exact sequence, and this UQ is surjective, so that's why corresponding to every element of CQKL there must exist an element of CQK. Okay, so in this case we are taking two elements just to show the well-definedness of this partial star. Okay, so Z is equal to C plus CQL. So why we are taking the elements of this form? Because we know that the CQKL, so the elements of CQKL, so this is equal to CQK quotient with CQL. So that's why the elements of CQL will be of the form elements of CQK plus CQL. Okay, so that's why we have this, and from this equality, so C plus CQL is equal to C prime plus CQL. So from this equality we can say that C minus C prime belongs to CQL, and also partial Q of Z is equal to 0. So now why partial Q of Z is equal to 0? Because we have taken this Z to be an element of HQ of L. Okay, so Z is an element of HQ of L. In other words, Z is an element of ZQ of KL. Okay, so Z will be of the form, let's say there is Z prime plus BQKL. Okay, so how to okay, so this Z, okay, is equal to Z prime plus BQL, and when we apply partial on this Z, so how to take image of this? So we have already seen that when we are taking the boundary of the elements of CQKL, then we are just using these boundary maps. So in other words, if this belongs to the kernel of this, so the image of this must be equal to 0, because by definition this must be equal to 0. Okay, so that's why partial Q of Z is equal to 0. Okay, so very simply, Z belongs to the kernel, so that's why the image is 0. And so partial Q C and partial Q C prime belongs to CQ minus 1L. So once again, these partial basically are elements of so these chains. Okay, so these are the boundary maps of this chain. Okay, so C and C prime are elements of CQL, and we can apply these boundary maps, and of course they belong to CQ minus 1L. Okay, now from the condition that this is a chain complex, so C and C prime are elements of CQL, so when we apply 2 times these chain maps, then we should get 0. So that's why we have this, and hence partial QC and partial QC prime belongs to ZQ minus 1L, of course. So these, okay, so C and C prime belongs to CQL, and partial C and partial C prime belongs to this, because they belongs to the kernel of this thing. Also partial QC minus partial QC prime is equal to this thing, so we are just using the homomorphism properties, and this belongs to the boundary of this, because C, once again, C minus C prime belongs to CQL, and when we apply this, then we get element of CQ minus 1L. So in particular, the image belongs to BQ minus 1L, so the elements of BQ minus 1L are the image of the elements of CQL under partial Q. So BQ minus 1L is equal to the image of partial Q. Okay, so or in other words we can say that partial Q of CQL. Okay, so so now partial QC plus BQ minus 1L is equal to partial QC prime plus BQ minus 1L. So this is clear from this case. Okay, so consider this portion and this portion. So partial QC minus partial QC prime belongs to BQ minus 1L. So of course this implies the classes. So if their difference belongs to this, then their classes, so BQ minus 1L must be equal to partial QC prime plus BQ minus 1L. Okay, so that's why we have this, and so we have the same image. Okay, so so partial Q of C and partial Q of C prime, so they have the same class inside CQL. Okay, so in other words, what we are saying is, so partial QC class and is equal to partial Q C prime class inside, so these are elements of HQ minus 1L. Okay, so there is a well-defined homomorphism from ZQKL to HQ minus 1L. Also the subgroup this is contained in the kernel of this homomorphism, so we have a well-defined homomorphism. Okay, so that's how we have this map which was given in this statement of this theorem. This is well defined. Now we have simple corollaries of our result. So corollary number 1 says that if we have a simplicial complex K and a subcomplex L, and if this condition is satisfied that HQ plus 1 KL is equal to HQ KL, so basically HQ plus 1 KL, okay, up to so on. So if this is 0 and HQKL is 0, then this is an isomorphism. So basically if these are 0, then we have this picture, HQL goes to HQK, okay, to 0. Okay, so and also we have proved that this is an exact sequence. So the image of this partial star and I star, and this is partial star, sorry, this is Q U star. So the image of this partial star is equal to kernel of this partial star. So the image of this is 0, so the kernel of I star must be 0. In other words, this is 1 to 1. Okay, so this implies it is 1 to 1. Once again, the image of this must be equal to the kernel of this. Okay, so the kernel of this is the whole HQK, and it must be equal to the image of I star. So in other words, this is onto as well. Okay, so let me write down again. So the image of I star is equal to kernel of U star, but kernel of U star is HQK, because everything in HQK is going to 0. So that's why this is equal to HQK, and if the image of I lower star is HQK, so that's why this is onto. So if it is 1 to 1 onto and it is homomorphism, so that's why this is an isomorphism. And similarly, if we have the condition that HQK, okay, so this thing and HQ minus 1K, so HQ, so this is HQ minus 1K. If this is 0, then this HQKL to HQ minus 1L is isomorphism. Okay, so using the same arguments, because this is 0 and this is 0. And once again, if we have HQL is 0 and HQ minus 1L is 0, then this is an isomorphism. So let's see how these results apply to calculate homologies. Okay, so if we have a simplicial complex consisting of all faces of an n-dimensional simplex, okay, so we have a simplex and consider all faces of n-dimensional simplex. So for example, consider this two-dimensional simplex, and it has 1 2 face and 3 1 faces and 3 0 faces. And so the collection of all this will be our simplicial complex, and we have already seen that it is not the same as just considering this 2 simplex, which is the triangle. Okay, and L be the subcomplex consisting of all proper faces of this simplex. Okay, now for example, the dimension of K is n, then when we are taking L to be a subcomplex consisting of all proper faces of this simplex, then of course L will not contain any simplex of dimension n, and it will only contain all the simplices of dimension n minus 1 or less. Okay, so in other words, what we are saying is Cn of k is of course non-zero, but Cn of L is equal to 0 because there is no n-dimensional simplex in L, because it contains proper faces of this of k. Okay, so but there is only one simplex of dimension n in Cn of k. Okay, so that's why we can say that this is isomorphic to Z, because there is only one simplex of dimension n. So it is free abelian group of rank 1. Now since L is a subcomplex consisting of all proper faces of this simplex, and K is a simplicial complex consisting of all proper and improper faces of some n simplex. So in other words, when we go to dimensions which are not equal to n, then they are equal, because they have the same elements. Because the only difference between CQL and CQK is that CQK contains one improper face as well, which is the simplex itself, and CQL contains all the proper faces, and that's why CQL and CQK are same whenever Q is not equal to n. Okay, so therefore we can write CQKL is equal to CQK quotient CQL is equal to 0 whenever Q is not equal to n, because they are equal. When they are equal, so their quotient is 0. Also CNL is 0 and CQK is isomorphic to Z. We have already discussed this, and so we have CNLKL isomorphic to Z. Okay, so once again this is just quotient of C and K and C and L, so that's why isomorphic to Z. Hence we have this result. So why this result? Because starting from Cn KL going to Cn minus 1 KL up to so on, so this is coming from 0 and Cn minus 1, so all the elements are 0. So we can say that what is Hn of KL. So in other words, what we are asking is what is the Zn of KL quotient with Bn of KL. So what is Bn of KL? So there is 0 over here, so the only element belonging to Bn is 0, because this is homomorphism. So the only elements which are images of some maps of partial n plus 1 is 0, so this denominator is 0, and Znkl. So since every element is going to 0, because Cnkl is 0 and every element is going to 0, so Znkl is Cnkl. Okay, so this is in fact equal to Z quotient with 0, and of course this is Z. Okay, and all the elements as HQKL are 0 due to once again the same reason, because every other element is 0 in this sequence. Now we also know that if from lecture 13, if K is a simplicial complex, and suppose that there exists a vertex W of K with the property that if vertices this span a simplex of K, then so do W V0 V1 up to VQ, then this homology is isomorphic to Z, and all the other homologies are 0 whenever Q is greater than 0. Okay, so coming back to our example, when we were discussing this, and K is a simplicial complex consisting of all faces of an n-dimensional simplex, proper and improper. So in this case we must have HQK is equal to 0 for all Q greater than 0. Okay, now using this result and using the corollaries, so now we have HQK and this HQ minus 1K, all these are 0, so we can say that HQKL is isomorphic to HQ minus 1L. Okay, so this is an isomorphism using the corollary. So in other words, we can say that HNKL is isomorphic to HN minus 1L. Okay, so and we have already seen that this is isomorphic to Z. Now in particular we can consider the case of n is equal to 1, so just one dimensional simplex. Okay, so this H0 of K, Okay, so we have already seen that h naught of k is isomorphic to z. So once again, using this proposition, okay, so h1 of kl, we have already seen that this is isomorphic to z. Once again, using this previous discussion, that this is isomorphic to z, and in this case n is equal to 1. And from the exactness of this sequence, so once again we already know that this is an exact sequence. So from the exactness of this sequence, this middle element h naught of L must be isomorphic to z plus z. So this is coming from our discussion of exact sequences, that if we know this element and this element, and what about this element? Okay, so this is basically one of the solution of this problem, is that this is z plus z. So this is also compatible with our discussion about the homologies of path connected components. So for example, if we have a simplicial complex L which has two path connected components, then its h naught of L must be isomorphic to two copies of Z. Okay, so basically this is a corollary of the results that we did in a lecture where we were calculating the h naught of a connected components. Now our next discussion is collapsing. So if K is a simplicial complex, a principal simplex of K is a simplex of K which is not a proper face of any simplex of K. So for example, V naught is not a proper face of any simplex of K, so it is a principal simplex. So in this case we have once again V7. T1 is not proper face of any simplex, T2 is not proper face of any, E1 is not proper face of any, E2 is not, E7 is not. Okay, so but V6 is proper face of E7, so V6 is not principal simplex. Okay, now for any sigma belongs to K, a Q simplex which is a Q simplex in K, a Q minus 1 face of Q minus 1 face tau of sigma is a free face if it is not face of any other simplex in K. Okay, so let's for example consider this T1 which is a principal simplex. Okay, so in this case this E4 is a free face because this E4 is not a face of any other simplex in this simplicial complex. Okay, so similarly you can find that this E5 is not face of any other simplex other than this T2, so E5 is basically free face of this T2. So what is collapsing? So suppose that a simplicial complex K has a principal simplex sigma which has a free face tau, then a subset L of K obtained by removing sigma and tau is a sub-complex of K and is said to be obtained from K by an elementary collapse, and this is denoted by K collapse to L. Okay, so for example, we have this simplex T1 and basically it has an free face E4 as well. So when we remove this T1 and E4 and when we remove this T2 and E6 because E6 is also a free face, and when we remove this E7 and V6 because V6 is not face of any other simplex, so that's why V6 is basically free face of E7. So we can do all these three collapses and we will get this simplicial complex. Okay, so if we have two simplicial complexes and we obtain one simplicial complex from another simplicial complex by this sequence of collapses, then we say that two simplices are combinatorially homotopy equivalent. So for example, if we have this two simplex and we can collapse this edge, and because this edge is basically face of this two simplex and not face of any other, so we can collapse this thing. Okay, and we get these two elements. Similarly, we can collapse this edge because this edge with this vertex because this is a free face, and we get this. And similarly, we can collapse this element, this face. This is a proper face, a free face of this edge, so we can collapse these two and we get this one point. So a 2 simplex which is combinatorially homotopy equivalent to a point. Now we have this result that if we have 2 simplicial complexes K and L which are combinatorially homotopy equivalent, then HQL is isomorphic to HQK. Okay, so here should be K over here. So the proof of this is provided in the lecture notes, and it's relatively simple. Next time we will see how to use all this discussion to calculate the homology. This is the end of the lecture. Thank you very much, and Allah Hafiz.